Alright, so today's topic is the E2 elimination. So let's take a quick look at what that looks like. So if you see something like this, where you have an electrophile, in this case we're talking about a haloalkane, and that's just an alkane with a halogen substituent over here. And then if there is a hydrogen located beta to the halogen, then what could happen if you have a base is the following reaction steps. So first, the base will deprotonate at that beta hydrogen. We'll talk a little bit more about what that means, and that will cause the electrons here to move into this region, and this bond will break, and the result of the final arrow pushing will look like this. Okay, so that is a lot to take in all at once, so we are going to take a much closer and slower look at what is happening within this. So first, again, this is called an E2 elimination, and in an elimination, well, let me spell that right first. You lose something on the substrate. So again, whenever we use the word substrate, we're really referring to this organic molecule here over here that is our reagent. So this is the substrate, it's also the electrophile. And we are losing a hydrogen, and we're also going to be losing this chlorine over here. And in this case, we gain a double bond. Okay, so that's what we mean by elimination. Alright, so why does this happen, and why does it happen in this sort of way? Well, hopefully you remember back to the first few lectures that hopefully you took in your organic chemistry course, and it goes back to bonding and anti-bonding. So if we have two orbitals here that are combining along this axis here, and they combine out of phase, they will be a sigma star, and if they combine in phase, as how you're used to, they will be a sigma bond. So we have sigma bonds and we have sigma star bonds, okay? Sometimes these are called anti-bonds. Well, let's talk a little bit more about that. So hopefully you also remember that whenever you form a sigma bond, you also form a sigma antibond. To be more precise, if there is a sigma bonding orbital, there also exists a sigma antibonding orbital. Now typically the sigma bonding orbital will be filled and the sigma antibonding orbital will be unfilled. And in this diagram, they're actually both filled. But let's apply that to the actual system that we're looking at. So let's take a closer look at this haloalkane species over here. Alright, so here, if we're going to look at this section, let me actually just get the picture of this so you're not completely confused by the balloon animals that are on there. So again, this was our original haloalkane. Here we're looking at the bonding that is taking place. So on this sp3 hybridized carbon, there's an sp3 orbital outstretched toward the Cl, and in the Cl, since it's terminal, it's a non-hybridized, it has a p orbital. And these two orbitals are forming the sigma bond. So along this axis, there is the sigma bond. Remember, whenever there is a sigma bonding orbital, there also exists a sigma antibonding orbital. So again, it's sp3 hybridized carbon, and over here, this chlorine is using its p orbital. So here they are out of phase. So what I'm saying is that you have the sigma antibonding orbital located over here. Okay, now a key thing to note is the sigma bonding orbital is filled. Let me try to spell that right. Let me try to move this. Sigma star antibonding orbital is empty. Okay? And they're located in pretty much the same region in space. You'll see that as the sigma bond is located over here, the lobe of the sigma antibonding orbital is on the back side of the sigma bond. Now, remember, whenever you have a sigma bonding orbital, you have a sigma antibonding orbital. They must exist as a pair. But this is filled and this is empty. Okay, let's sort of look at the ramifications of that. Okay. So I'm sort of going through this slowly because this is pretty hard for a lot of undergraduates to understand, but it is incredibly important. Okay, so focusing back on this diagram, the reason I have this filled is because I want to make a point. If you remember back to bonding order, if you have the sigma filled and the sigma star filled, your bonding order is 0, and you actually have a collapse. There is no longer a sigma bond, the bond fails to exist. If you look at, say, helium-2 as a diatomic species, that's why it doesn't exist. Now, what I'm trying to say is if you put electrons into the sigma star orbital, you severely weaken the sigma bonding orbital to the extent that it will actually break. So let's look at that in relation to, once again, the system that we care about. So here we're having the base attack the hydrogen right here. Now what that will do is that will move the electrons from this bond down to this carbon. That should be something you've seen before. Nothing too crazy about that. So let's look at this hypothetical transition state. We now have electron density located at this carbon. If you remember back here, the empty sigma star orbital is located here, and the lobe of that antibond is actually right there, right next to the electrons that were just transferred there because of the base deprotonation. Okay, so what could happen is that these electrons that just came from that bond, the bond to the H that was just, well, removed because of that base deprotonation, those electrons can donate electron density into sigma star. And as we just talked about before, the bonding order will go to 0. What that means is that the sigma bond will weaken dramatically. What that does is it causes this bond between the chlorine to the substrate to break. As a result, you get your final product, which is going to be the alkene. So the pi bond will form here, and you'll be left with your leaving group hanging out in solution, as well as, in this case, H2O. Because we had hydroxide as a base, when it takes an H, it'll become water. Okay. So what are the key points? Well, first thing we want to discuss is the fact that the E2 mechanism is concerted. What do we mean by concerted? Concerted means that the bond formation and the bond breakage occurs at the same time. So looking back up here, the bond formation here and the bond breakage occur in the same step, which means this all happens at the same step without generating an intermediate. You get a transition state, but you don't get an intermediate. Remember the difference between that. So if we had a reaction coordinate that looked something like this, and we have this, you of course know your reactants over here and your products over here, but at the top of this hill is your transition state. Now, if you have something like this, this is a transition state, but this little valley here is an intermediate. What we're saying is that since this is a concerted mechanism, no intermediate is formed. You only get a transition state. Intermediates are possible to isolate in the lab. Transition states are not. They're short-lived, so short-lived that they actually, they can't be isolated except for by spectroscopic methods. So because this is concerted, the rate of this reaction occurring depends on both the substrate and the base that you use. We'll talk about that a bit more later. That's pretty important. In fact, it's so important that that's the reason why E2 is called E2. E2 stands for elimination, second order, and the fact that it's second order comes from this rate expression over here. So the rate is dependent upon both the substrate and the base. each of these in the first order. So if you want the overall order of the reaction, you add the exponents. So substrate to the 1 plus base to the 1 is 2 overall. And lastly, the E2 elimination is favored by entropy. Now what do I mean by that? Well, let me go back up here. So notice that on the left-hand side, we have two molecules. We have the substrate and the base. And on the right-hand side, we have three molecules. We have the protonated base, the leaving group, and the substrate. We have generated a greater number of molecules in this reaction. What that means is that the entropy increases. Now, if you remember your thermodynamics, you should remember this big equation. So if the elimination is favored by entropy, that means increasing temperature will favor elimination. Right? Remember, the more negative your delta G is, the more spontaneous a reaction is. So this is one big reason why, when you get to substitution versus elimination, more heat will favor elimination. Okay, now let's look back at those orbital arguments again, just for another second. Okay, so here we have a similar kind of setup going, but still pretty different. So let me get this back up here so we have something to reference. This was the original molecule we're looking at over here. This is the new one. So notice that the H is no longer up here, the H is down here to the left. So this time, as the base comes in and deprotonates, the electron density will go in this region over here. Now, look at the problem here. Remember, the entire reason that this E2 elimination worked is because there was electron donation into the antibonding orbital here. Now, if your hydrogen is located on this side of the molecule, then the electrons will go into this region here. The problem with that is that these electrons cannot donate into the antibonding orbital. So, the reaction cannot proceed this way. So, from the bonding arguments, we're able to get a stereochemical reason, or a stereospecific reason, why E2 cannot proceed in this fashion here. In other words, we require that the hydrogen that is being taken off the substrate, that the base is actually abstracting, must be anti to the leaving group. So if we look back here, the hydrogen over here is anti to the leaving group. It's on the opposite side of the molecule. The reason for that is because when this deprotonation occurs, the electron density must exist within this region because the antibonding orbital is most prevalent in this location. If you don't have the anti relationship between the leaving group and the hydrogen, then E2 elimination can't happen. Another result of that is that these two orbitals need to be in the same plane. So the electron density that's collected by this carbon after the deprotonation must be in the same plane as the orbital that has the antibond. Otherwise, geometrically, it's not possible for the E2 elimination to occur. So again, the reason why the E2 elimination must occur with so-called anti-periplanar or anti-coplanar geometry is this entire orbital bonding argument, that the electron density that comes from the base deprotonation must be able to reach the antibonding orbital, which will weaken the sigma bond there, causing it to break. Okay, next time we're going to do actual examples on how to do the E2 elimination.